Welcome back, future computational chemists. Today, we're moving beyond the console. You know that feeling when you run a complex calculation, get the perfect result, and then close the program, and it's gone? Yeah, it's a heartbreak we've all felt. Today, we fix that. We're learning how to store data temporarily and permanently, even after the program ends. We'll learn to tap into external files like .txt, .csv, and .json. Because let's face it, if your research isn't saved, did it even happen? In Python, the skeleton key for everything related to files is the open function. It's pretty simple. It needs two things: the file name or path and the access mode. Think of R for read, which is the default. Then there's W for write. This creates the file if it doesn't exist. A quick warning, W is a bit of a terminator. It will overwrite everything in an existing file without asking. Let's say we have a file called mydata.txt with some elemental info: carbon, symbol C, mass 12.01. We have a buffet of ways to consume this data. The whole hog. Read, this returns the entire text as one giant string. The one-liner. Read line. This reads just one line. If you need more lines, just repeat it using a loop with a placeholder underscore, the universal Python symbol for "I need a loop here, but I don't need to name the variable." The list maker. Read lines. This returns your data as a list of strings, including those pesky \n newline characters. The most professional way to read a file line by line is simply looping over the file handle. This method is lazy, and in programming, lazy is a compliment. It doesn't load everything into memory up front. It reads each line on demand. It uses a cursor to track its place, so once the loop finishes, the cursor is at the end. If you try to loop again immediately, you'll get nothing. The party's over. So far, I've been a good citizen and used f.close to free up system resources. But honestly, humans forget things. We forget our keys, our lab goggles, and we definitely forget to close files. Enter the with statement. This invokes a context manager. It's like a personal assistant that follows you around and cleans up your mess. As soon as you exit that indented block, the file closes itself. This is the preferred professional method. Time to create. Let's say we want to map out some quantum subshells. We'll use the W mode to write our orbitals.txt. Example, suppose we want to create a file, orbitals.txt, in a folder data and write orbital symbols for angular momentum quantum number L. After running the script, data/orbitals.txt contains L orbital, 0, S, 1, P, 2, D, 3, F. Now, you might be wondering, should I use f.write or print file equals? Write is for the control freaks. It adds nothing extra, no spaces, no new lines. If you want a new line, you must add \n manually. If you want to write a number, you have to wrap it in stir. It's perfect for scientific results and structured logs where every character counts. Print file equals is for the convenience seekers. It handles the formatting, adds new lines, and converts numbers for you automatically. It's great for quick reports or teaching examples. Rule of thumb: need surgical precision? Use write. Need to get a report done before the lab meeting? Use print file equals. In part 2 in this video, we'll apply this to a real chemistry project, enthalpy calculation. All right, enough syntax. Let's do some science. We're going to build a script that reads a library of enthalpies, parses a chemical reaction, and calculates the total reaction enthalpy using Hess's law. First, we need to load our data from enthalpies.txt. But wait, real files are messy. They have headers and empty lines. Let's look at how we handle that. We use .strip to clean up whitespace and line.starts with hashtag to skip those header comments. We then split the line into the chemical name and its value. Remember to use float. Python can't do math on text. Now for the big brain part, parsing the reaction string, like CH4 plus 2O2 produces CO2 plus 2H2O. We need to separate the reactants from the products and identify the stoichiometric coefficients. We split the reaction at the arrow. Inside our parse side function, we split again at the plus sign. If a compound has a number in front, that's our coefficient. If not, we assume it's 1. This allows our script to handle any balanced equation you throw at it. What if you have 100 reactions to calculate? We don't do that by hand. We use a double context manager to read from one file and write to another simultaneously. We read the reaction, calculate the delta H, and use outfile.write to save the result. Notice the 0.1 F. That's just to keep our decimals tidy for the lab report. And just like that, you've built a tool that can process thousands of thermochemical reactions in seconds. You've gone from student to developer. Try downloading different enthalpy datasets and see how your script handles them. Now go forth and make your data immortal. See you in the next one. Always use with to keep your resources safe.